So in the flavor of many of the discussions we have had across the 3 days, today I will focus on what we have been doing in the area of time and space-time metamaterials. And this actually connects nicely with this picture that maybe some of you from previous years have seen already. That was the vision we had in the initial proposal on the Simon's collaboration. In particular, the idea of bringing together symmetries, and in this case, bringing together the tools that we have developed over many years in the context of metamaterials in space, geometries, with dynamical symmetries, and leveraging the two in a unified manner to unveil new forms of extreme wave interactions. In fact, at lunch we were saying how many of the initial hypotheses that we had in the proposal are actually now coming together and unifying this vision of symmetry-driven wave phenomena. This is also what we've written in this kind of perspective paper, in which these fields of metamaterials and the parallel field of Floquet matter, out of equilibrium materials, are coming together, leveraging really space and time in a unified fashion. And you have seen many examples of this from the first talk of the whole event, from Vlad to the most recent talk from Francesco, the powerful opportunities that come from using all these tools in a kind of smart way. You have seen also this slide from previous presentations here in this meeting. I will use this a few times, so I wanted to bring it back also this year. The idea, of course, of having a discontinuity in space is that the conservation laws in this case are the ones of frequency and energy if the system is lossless, is Hermitian, but you have control over momentum, and that's a summary of what you get by leveraging spatial scattering. The dual of this is the temporal scattering, so when we have abrupt changes in the material properties in time that are uniform in space, you conserve translation invariance, then it's the momentum to be conserved. And whereas there is an agile form of manipulation of the frequency and energy content that comes from non-dynamic out of equilibrium responses. And to achieve that, as you will see a few times during the talk, we really need to be able to change in an abrupt and uniform form the properties of the material. So our first platform for demonstrating some of these has been this microwave transmission line. I will delve a little bit more into this in the next slides. Basically, the idea is that you have a strip of metal on top of a ground plane, and you load it with these capacitors that are switched on and off in a fast way compared to the variations in time of the structure. This is how the first board we built looks like. It's already a couple of years old, but the idea is to have this dense array of switches that load and unload capacitors as an extra dimension to change effectively the index of refraction of the material, in particular the impedance. So if you look at the physics of this comes from textbook material. If we have a strip of metal on top of a ground plane, of course we have inductance that comes from the currents and the magnetic fields around the strip, and the capacitance that comes from the charges between the top metal strip and the bottom ground plane. And in fact, in electrical engineering language, we describe it with this model of a distributed transmission line with series inductance and parallel capacitance, and the effective permittivity and permeability are connected to the capacitance and inductance per unit length. Many of you, of course, are very familiar with this. What we do in this demonstration is to add capacitance in a dense spatial way and connect them through switches, electric switches that can be activated very fast. We don't change the capacitance in time, that is a much slower process because of inertia of the material, but we just connect and disconnect these reactive elements. This gives you an effective permittivity in the limit in which these are denser than the wavelength that is transformed through this formula, in which this is the capacitance of each switch, and this is the distance between them. So it's a simple homogenization. And you can see from this formula that I can switch on and off a capacitance per unit length or a permittivity that can be much larger than the original capacitance of the line. And that's how we can get a large contrast in permittivity in a very fast time. So the result is this abrupt switch between two dispersion, and if you achieve it fast enough, you preserve momentum. So in the momentum frequency dispersion, you can have these vertical transitions in which you go from, if you are from the off, these are, by the way, experiments and simulations. You go from the off to the on case. You can actually abruptly change the frequency content of the wave, and also couple, if you do it fast enough, to the negative branch, negative frequencies that provide this tool for time reflections. This is what creates this broadband and efficient time reversal across the entire content of the material. Of course, the important aspect here is that this has to happen uniformly in space to get these vertical transitions. It has to happen fast enough to enable this jump from positive to negative frequencies in the energy diagram. And these are experiments that you've already seen, in which we see this broadband stretching of the signal and time reversal. If it's an asymmetric signal, it gets reversed in time. The time refraction at the output port is just a stretching of the material without distortion. And you can see this better in Fourier, in which you can see that the reflection and transmission coefficients in time are flat across frequency or momentum, and that you have this stretching of the time axis because the frequencies are halved all across. So in this case, the index of the material was increased by 2 times, and that's why the frequency goes down by a factor of 2. If you combine 2 of these time interfaces, you create a similar phenomenon as the one of the Fabry-Perot in space. In this case, it's a momentum Fabry-Perot, and you do get beating in momenta, in which some momenta have 0 reflections, some other have peak in reflection. You have seen this already as well. But this allows me to build on what we have been doing in the past year on this front. The first aspect is, can we push this to higher frequencies? This is a CMOS implementation of a similar board. It's much smaller. The whole thing is just 5 centimeters, and it's an integrated circuit. It's done in a foundry. We can lower the gain, an array of switches. Now it's also a smarter implementation in which we can control independently groups of switches, so we can create also stuff like what we have seen in past years from Matthias Fink's group of moving interfaces or other forms of more sophisticated space-time metamaterials. But here you see that we can access a few gigahertz regime, and we can observe a similar broadband phenomena for single or multiple time interfaces. And this opens to the opportunity that was already introduced theoretically by Francesco in the previous talk of looking at the dual of a photonic crystal rather than having periodic modulations of the permittivity or the index in space that creates frequency bandgaps in which the waves decay exponentially. We can find this dual phenomenon in which momentum bandgaps open up and in which the waves actually can be amplified, can take energy out of the modulation scheme and realize this momentum selective amplification. So in this structure, the physics is a little bit different, and actually this is interesting. Francesco mentioned the difficulty in achieving this phenomena because of requirements on energy. Interestingly, through a switch, you cannot really pump energy into a material because a switch looks like an open or a short circuit depending on its state. So both states do not allow energy transfer to the wave. And in fact, if you calculate the photonic crystal band structure of a periodic modulation of our circuit, what you find is something very similar to the band structure of a photonic crystal, but in which the imaginary part actually has an offset from the real axis. And as you see, any wave number, the imaginary part is always positive. This is physically due to the fact that you cannot pump energy through a switch, but you do get momentum gaps. And in fact, the point that would have the maximum amplification, that is actually the point that wins, that gets you the momentum selectivity of a photonic crystal is the point in which the signal is completely preserved. It doesn't experience any loss that is otherwise incurred due to the fact that capacitors are being switched on and off when they have a charge on their plates. And you can see this here. If you excite in band, after few switching events, the signal is completely absorbed because of the finite imaginary part of the signal. But if you do it in a band gap, then actually you transform a forward wave into just its component that sits at the bottom of this point with the standing wave response, with the forward and backward. So here there is no amplification. There is momentum selectivity similar to the one you get in a photonic crystal. But this doesn't require any energy to be run. How about pushing it to even higher frequencies? We've been working quite hard on this in the group to leverage materials. We have seen the beautiful talk of Vlad 2 days ago, and Marcello and their experiments in the context of oxide materials. Here we've been looking at a regime in the range of tens of terahertz, so in the mid-infrared range, using highly doped indium arsenide that supports this zero permittivity region that again helps, as Vlad showed us beautifully in his presentation, allows us to enhance nonlinear interactions with the material. We excited with a pulse that is less than 20 femtosecond wide, and the advantage of working in a regime that is optical but it's still pretty low frequency compared to the visible frequencies, that now we can actually access sub-cycle modulation. And indeed we see quite sharp dynamics in the reflectivity of the material as we heat it with this pump. These are very recent measurements from Romain, that is in the audience, in which we do have indeed a fast sub-cycle response with a pretty large amplitude of modulation of the frequency. So we are observing time refraction. We believe that we are in the regime in which we can observe also time reflections, and that's something we plan to do soon. We are also using a quite modest intensity compared to other experiments, and yet we get a strong response. So we're optimistic that this is actually an interesting platform for observing this phenomena at optical frequencies. Now, one thing that this led to, and this is also in collaboration with Nader and Geta, is the idea, if we like to work with these ENZ, these plasma-like materials, can we actually explore what is the physics in these materials using our tabletop platform that is our transmission line circuit? So how do we make a plasma, an ENZ material at microwave frequencies in this tabletop implementation? I go back to this picture that I was telling you before. This is our strip line. If instead of loading it with a capacitor, I load it with an inductor, this inductor, through simple equivalence between reactances, can be seen as the equivalent of the capacitor, but with a dispersive response. It's a -1 over omega square L. And as you can immediately see here, this implies that our transmission line, if we load it with a shunt inductor rather than a capacitor, becomes a Drude material with a cutoff similar to an ENZ material, very similar physics, but now with a lot more opportunities to speed up, I guess, the ionization of your plasma through just switching on and off your inductor. So this is the board that realizes this effect. And the two things that I speculated on in a couple of Simon's meetings ago, and that we are now observing experimentally, but I don't have time to show you, is conservation of imaginary momentum. If you excite the structure below the plasma frequency in which they doesn't support a wave, you can actually conserve imaginary momentum. And giant frequency conversion, if you work at close to the ENZ, the wavelength is very, very long. So if you can start from very low frequencies and actually upconvert as you switch on and off the plasma response. These are two exciting developments that come from a platform like this. Now, connected to this, a byproduct of conservation of quantities that comes from symmetries is that in a spatial scattering, you are very familiar with the usual conservation law that comes from time invariance. That is that the sum of reflection and transmission is equal to 1 in the absence of loss. In our temporal scattering, conservation of translational invariance and of momentum gives you this other law that is different from before. Here, as you see, T and R are actually unbounded. You can get large amplification if you do things right. But what's interesting is that you cannot get reflection without increasing transmission, because the difference of the two is 1. That's simple to understand. If I want to have a reflection, I subtract momentum, I need to pump other momentum to the forward wave on the other side. And actually, already when we did the first experiment, the student Adi Musa that led that effort, when he was defending a PhD, one of the committee members asked, can I get full reflection? That's what I really would like. In fact, Professor Engeda has shown this with non-Foster elements. He was showing also yesterday. We have been exploring other ways of, in some ways, breaking this necessity of pumping energy in the forward direction if I want time reflections. So the question is, can we achieve full time reversal without breaking translation symmetry? This question, by the way, was started the discussions in the last Simon's meeting. I think I was sitting line in front of Yevgeny and Jacob that were asking what opportunities there are by playing not with phase velocity but group velocity. And then we worked with Jacob on this problem when he visited us last spring in his sabbatical at SRC. And this is the platform that we studied. Again, it involves a plasma. And this is, by the way, work also with Luca Stefanini, that is a postdoc in our group. So here, we don't want to break translation symmetry. Of course, if you break translation symmetry, you can use a mirror to time reverse, to reverse the flow of energy. The question is, can I do time reversal without breaking translational symmetry? But rather than requiring very large abrupt time variations, so large frequency transformations, can I leverage coupling, adiabatic coupling between modes with different group velocity? So this is a plasmonic waveguide that supports, this is a standard dominant mode of this waveguide. It has a permittivity less than 0 in the middle. So the interesting aspect of this waveguide that has been studied for many years is that the power flow in different regions of the waveguide is opposite, right, because of the change in permittivity. So the net power flow that determines the group velocity, the direction of propagation of the mode, is the difference between the flow outside to the flow inside the medium. And you can see this here. These are different curves in which, dispersion curves again, momentum versus frequency, in which we are changing the plasma frequency. So we are modifying, this can be done in an adiabatic, very slow fashion, the dispersion of the plasma material. And as you see from this plot, as at fixed momentum, these vertical transitions that are associated with preserved translational invariance, you can move from a dispersion that has a positive slope, group velocity, to a negative slope dispersion. What this essentially boils down to is that as the plasma frequency changes, you are squeezing the mode inside this region, and therefore from a power flow that is mostly outside and therefore is positive, you get to a power flow that is actually mostly inside and therefore negative, and that changes the dispersion of the flow. So notice the important ingredient of breaking out-of-plane symmetry to achieve this effect. And you can see this here. You have a power flow that as a function of plasma frequency can go from positive to negative, but actually quite remarkably, the momentum of the mode does not change sign. And that's because the momentum that you conserve is Minkowski momentum, and the Minkowski momentum is D cross B, it's not E cross H. So the fact that the permittivity here is negative actually preserves the flow of momentum in the three regions with the same direction. And that's why when you change plasma frequency, you actually preserve the positive flow of Minkowski momentum. Here, things are a bit trickier because also you have the possibility of coupling to a DC mode, the Wiggler mode of the system, that actually subtracts electromagnetic momentum from the problem. So the momentum, electromagnetic momentum does not need to be conserved. It's the total momentum to be conserved. And that's the mechanical momentum. Essentially, you are transferring, as you do this adiabatic change of plasma frequency, you transfer some of the momentum to mechanical momentum in the material DC mode. But interestingly, so this effect is mediated by this DC field that subtracts part of the energy and momentum. But interestingly, you can achieve full time reversal of a pulse that operates first in this forward mode. So this is the initial waveguide is traveling in one direction. And then by slowly changing just the group velocity. Here you don't need to do this very fast change to couple to negative frequencies. You're just changing the group velocity. Actually, the mode is reversed. And it also, in principle, would, if there were no loss, would actually compensate the distortion that you get naturally from the dispersion of the material. And this also you see in analytical and simulations of this problem. So a very slow change of permittivity around this point in which the group velocity flips sign can enable full time reversal of the system without breaking the necessity of conserving forward momentum, Minkowski momentum of the system. So conservation of Minkowski momentum does not prevent full time reversal. There are also a lot of connections with the discussions on Abram versus Minkowski. That's another story. You can do even more if you assume that you can actually abruptly switch the plasma frequency. So I showed you now very slow changes in which you are not coupling to negative frequencies. If you can couple to negative frequencies, you can actually leverage this coupling of momentum from electromagnetic to mechanical. And if you time it right, so if you have a temporal slab of the right duration, and you exploit this idea that part of the momentum can be actually cancelled by the form in which you actually switch the plasma frequencies on and off, similar to what we do in our board, you can actually realize a full-time reversal without even having to break out of plane symmetry in a completely uniform medium. So in this case, you see it here from the total momentum here that, of course, it's preserved. You switch, you couple some of this to mechanical momentum. In a uniform medium, you must conserve total momentum. But the trick here is that you can actually dump the part associated to the forward wave by annihilating the part of the momentum that mediated by the mechanical. And the final result is that you get only backward wave out of the system. This actually can be observed in this board. Actually, switching on and off inductors is exactly the recipe you need to dump mechanical momentum out. And indeed, this is what we see. This is as a function of the duration of the temporal slab and the where the pulse is when the temporal slab is activated. You see that you can actually control the response to get mostly forward here, mostly backward on the other side. So you can break completely that rule that the difference of forward and backward is always the same. These are experiments in this board demonstrating indeed that you can get, we don't get exactly zero, but we get more backward wave than forward wave. That is actually remarkable because it violates the principle that I was showing you before about momentum conservation. And now I link to the second part of the talk in which I add the time to the picture. This also is a slide you have seen before. I was showing you last year some initial explorations. That was the first time we presented that work, and we've done a lot more in this area. That is the idea of using synthetic rotations driven by space-time modulations to access this regime of Penrose-Zeldovich super-radiance. Let me explain in a moment what we mean. We've been working for many years on the idea that by rotating a system in time, we can break reciprocity, we can break time reversal symmetry. And one convenient way we have been working on for several years to do that is to use temporal patterns of modulations that are chiral, that have a handedness. So this is a good example, a permittivity modulation that rotates with a finite non-zero angular momentum. One of the simplest implementations that we developed over the years was these three identical resonators that are modulated with different phase patterns to realize a synthetic rotation of the medium. We have built many non-reciprocal devices based on these principles. But the question that we have been trying to answer more recently is what degree of rotation can we achieve? In particular, can we synthesize on a tabletop experiment the vision of Penrose of many years ago of extracting energy from a rotating black hole by accessing superluminal regimes that couple to negative energy. The initial idea of Roger Penrose, I showed you also this slide last year, is that if I have a mass that falls into a rotating black hole, there is a region of the black hole called ergosphere that actually is connected to negative energy orbits. And if in this region I dump a portion of my mass in the black hole, I actually acquire a larger mass and get out of the black hole. This was, of course, a theoretical demonstration, a theoretical proposal that drove a lot of interest. In fact, also it spurred the ideas of Stephen Hawking on evaporation of black holes. Now, if we can synthesize rotation, can we use it for mimicking these responses for electromagnetic waves? Well, this is also a problem that has been explored quite extensively. In particular, Zeldovich has been the first to realize, as far as we know, that one can actually extract energy from a rotating body for classical waves. And the main idea is that if I have a disk that rotates at finite angular momentum, then by sending a wave onto it, the reflected wave can acquire energy, can be amplified, or can subtract energy from the rotation if it obeys negative rotational Doppler shift. So the idea, similar to what I showed you in the first part of the talk, is that I can access negative frequencies through Doppler shifts that are superluminal, and that allows you to extract energy from loss, basically. You are time reversing, loss is present in the disk that become gain and extract. So you need actually, it's a loss-mediated phenomenon. It's quite remarkable that if we switch off the loss, this system doesn't work. Now, the question is, can we do it? Beautiful talk of Emmanuel Forte yesterday showed us that water waves are a very good platform to do that. In fact, people have shown this phenomenon. Acoustic waves is another great platform for this, and many of our collaboration PIs are working in this area. In these problems, of course, the waves go sufficiently slow that one can access superluminal velocities by just rotating fast enough some media, with some complications, obviously. But these are beautiful experiments reporting the prediction of Penrose Zeldovich for acoustic and water waves. Now, the question is, can we do it in optics, or can we do it in electromagnetics? Of course, waves go much faster. By the way, I forgot to mention one thing. One caveat to realize less restrictive demand on the velocity required is to use orbital angular momentum. You probably have seen it already in these pictures here. If you send a rotating wave, you actually relax the conditions over the rotation. One challenge of that proposal is that, as you probably know very well, if I have high-order orbital angular momentum waves, they tend to have a big hole in the center. So to actually interact with a rotating disk, this disk has to be larger, and that requires still superluminal linear velocities at the edge of the disk. So there is a trade-off. You cannot choose a very large OAM, otherwise you need a very large disk, and that defeats the purpose of having a lower angular velocity. So there is basically some physics that you're fighting in these systems if you want to do it for fast waves like light. But one advantage we have is that phase velocity does not have a limit. You can spin much faster than light. You can speed at infinite speed, in fact. So the question is, can I translate the proposal of Penrose into a synthetic rotating circuit in which the things are all static, but they're modulated in time to mimic this rotation? And you can solve the problem analytically. I think I showed you the analytical solution last year. This is basically the result. If I excite with a certain frequency and a certain angular momentum, and I assume that the system is rotating at a certain angular velocity, this is a synthetic velocity based on the modulation pattern and with its own angular momentum, then the output has to obey these conservation laws. These are a bit the generalization of what I showed you before. Now we're changing both space and time, so we don't conserve neither frequency nor momentum, but we conserve these quantities that are algebraic sums of the two. But most importantly, I can realize these types of Doppler shifts that can access negative frequencies, and these are actually the byproducts of that. When I add loss, I would expect two things here. One is that the angular momentum is time reversed, so I send in one and I would see the opposite. And second, that I get gain. I get amplification based on time reversal of the loss in the system. This is the chart that ensures that these quantities are conserved, this generalized frequency momentum conservation law. If you work with the higher order effects, you can actually lower even the condition to access this negative rotational Doppler shift regime. This is actually the general formula of how fast do I need to modulate in frequency to access negative frequencies for any given order of the process. And these are the maps that we hope to see. These are actually very similar to the maps that the acoustics people have shown in their experiments. What you see is that my input signal is at this frequency. If I look at the product at the same frequency, of course, it's constant. There is no change in angular momentum nor in frequency as a function of modulation. But the Doppler shifted responses are actually a different angular momentum. In particular, this is the first order one that, based on the law I just showed you, flips from +2 to -2 in this case. But interestingly, as I access the negative frequency regime, it mirrors, basically this is the replica that comes in from here that has time reversed angular momentum and actually emerges from here with the gain. Right? This is lossy, and as it bounces off the zero frequency, it will have opposite angular momentum and gain. This is connected also to momentum gaps, but these are angular momentum gaps. So for slow modulation speeds, I have the usual frequency gaps. So this is frequency and angular momentum, and these are gaps in frequency because I'm modulating slow. The static case is the limit. These are non-reciprocal frequency gaps. We can access that. The beauty of this is that we can control the speed very easily by modulation signals. But if you spin faster than the velocity of the signal in the circuit or in the rotating circuit, you open momentum gaps with gain, with amplification. This is true amplification because we are using varactors here. So we can actually amplify the signal. And we see this also in experiments. These are the momentum gaps that emerge at specific angular momenta for specific modulation frequencies. This is how the first circuit we built looks like. It's a 3-ring resonator. We feed the modulation signals and the angular momentum waves that we send in and out of the system. It's a little bit convoluted experiments because you need also the modulation signals at signal generators. But this is what we measure. So at the fundamental frequency, nothing interesting. You get the same frequency you send in with the same angular momentum. But then if we look at the first order Doppler shifted signal, you see that as you monitor for different modulation frequencies, the signal, of course, is Doppler shifted down. This is a conventional Doppler shift, preserving the same angular momentum that you expect from conservation law. But as you hit the 0, you get to the other side in which there is no angular momentum for +1. You get -1 angular momentum, and you start seeing amplification. This is the map of the amplification. We measure about 10 dB of amplification for the time-reversed signal. And indeed, we also demonstrated that as you make the quality factor worse, you actually increase this net amplification because of the law I told you, that we are time-reversing the loss of the system for the same modulation frequency. And now, after that, we looked at Zeldovich paper again. This from, again, 50 years ago or more. And Zeldovich speculated that in a quantum analysis of the wave field, one should expect spontaneous radiation of energy and momentum by a rotating body. For the same reason for which we can extract energy when you drive it, we should expect in a quantum analysis that this system spontaneously emits momentum and energy out of this. This is also connected to the dynamical Casimir effect and quantum friction. There has been actually a lot of work in this area of spontaneous emission by rotating objects, mostly theoretical work. Now we have a platform to actually explore it. We don't mechanically rotate anything, but we're just spinning it through time modulation. And we basically are not driving the system. We're just looking at what it emits as we drive the modulation around it with the right speed and with the right frequency. So what we observe is that there is clear angular momentum selectivity of the emission. This is for a low quality factor array of resonators. This is when you add the quality factor, you get a more sharp, more coherent emission.
Looking at microwave radiation from your...
That's right. Yeah, this is basically noise. It's noise from the resistors. So it's not really, it's not quantum, obviously. It's just spontaneous noise that comes from the circuit. But we do see that there is a clear peak that is angular momentum selective, especially if you drive the system with a high Q resonance. And indeed, as you increase the modulation strength, you improve the coherence. The line width goes down, the coherence goes up. You see it here. And you get more emission, specifically in one OAM. The system becomes, of course, there is a little bit of leakage into the other OAM, but it gets better, more pure, as you drive stronger the modulation that gives you this synthetic rotation. These are measurements that indeed demonstrate this response. And indeed, we see also saturation at some modulation strength and preferential OAM. This is confirmed. And the line width that also is reduced gets more coherent. We can also observe things that were predicted for the rotating body. For instance, one aspect that was developed in the theoretical papers before is the aspect of quantum friction. Basically, the idea is that if my system emits, it should slow down the rotation. We cannot really see slowing down because here we are synthetically rotating. We're assuming that the velocity is fixed. It's fixed by our drive. But what we can measure is how much it takes to spin. And we do see that this actually grows. So this is the analog of quantum friction. It takes more energy to spin because we are emitting. Of course, it's power conservation, basically. We can also see the analog of squeezing. If we pump at basically, we look at the frequency that is different than the resonance, we do see this, looking at the properties of the noise, we see an unequal distribution of uncertainty between two quadratures, and indeed this is what we observe or predict. This is as a function of modulation strength, and basically if we look at the same mode, I don't see any squeezing, but if I look at quadratures for the different modes, I do see this squeezing of these states of the system in the two quadratures. The last thing that we've been exploring, we've been very interested in the last years, if I have a few more minutes, yes, in manipulating thermal emission. clearly this part of the experiments in which we're looking at spontaneous emission from these synthetically rotating bodies is related to these these random processes that happen naturally in materials that drive also thermal emission. So over the past years, we've been working on ways to structure materials in space to manipulate the way in which they emit thermally. This is driven by geometrical symmetries. Actually, these are all rationally structured surfaces. This is an example of actually an experiment that thermally emits with large temporal coherence, as you see from this bandwidth, a selected circular polarization. But of course, these types of spatial structuring of materials to modify the thermal emission states still obeys several constraints, driven mostly by time reversal symmetry. Again, conservation laws apply also here. In particular, you can prove, this is Kirchhoff's law, that the thermal emission from any structure you build, how complicated you make it, as long as it obeys time reversal symmetry, it must be equal to the absorption of the same structure for the conjugate field, the time reversed field that comes in. So basically, these types of spatially structured thermal emitters are selective absorbers that absorb only in this wavelength and only for this polarization, for the opposite polarization. Right? This is circular, so you should look at the opposite tenderness. Actually, recently, just out of curiosity, we took some of the structures that are chiral and we showed that indeed this works. These are independent measurements for emission and absorption, demonstrating that indeed the resonant peaks that come from these complicated structures indeed match one-to-one between opposite tenderness. It's something, of course, was known for decades, but from Kirchhoff actually, but we don't know that others have looked at it because it's typically very difficult to get this circular polarization selective emission in a structured material. But this basically is conservation law of time reversal. Now, there is a lot of interest in violating this law. Let me mention these are works from Harry Atwater and Shanhui Fan over the past years, in which by breaking time reversal symmetry, in particular by adding a magnetic bias, they have been showing that they can actually break this equivalence between absorption and emission because of the applied magnetic bias. Now, these effects are typically very small because it's difficult to get stuff that is strongly magnetic, strong magneto-optical responses and with a large sharp resonance. We have looked for several years at using time modulation to break this symmetry. In fact, this is an old paper in which we mapped that problem into the problem of an antenna that is modulated in time and that transmits without receiving. That is basically the same problem. And we did show this largely asymmetric response. Now, the question is, can we optimize and how far can we push this idea of violating Kirchhoff's law, of creating a system that absorbs without emitting at a certain part? To do that, Sander Mann and Dimitrios Sounas and I have been developing a general framework that extends Kirchhoff's law to time-modulated systems. The idea is that when you have a time-modulated system, predicting what you absorb or emit at a certain frequency is a bit more complicated because you have all the coupling between frequencies. If you assume that the modulation in time is periodic, then you create this ladder of frequencies that come from mixing. You can still write the full absorption at a certain frequency as the sum of all the absorptions at all frequencies that can mix through the modulation pattern. And interestingly, you can relate this quantity to the emission at the same frequency through a system that is conjugated in time and that is mapped to the I mean, you can relate basically the emission at one frequency to the absorption at all the frequencies that would contribute to that emission. And there are these scaling factors that come from the difference in thermal population at the different frequencies. So with this in hand, we can actually optimize a modulation pattern in time to maximally violate Kirchhoff's law. As we were doing this, we realized that our system of a synthetic rotating ring already does that, in fact, optimally. This is the measurement in absence of modulation. It doesn't emit much or absorb much, but of course they are identical. When you start modulating, you do get a drastic difference between absorption and emission for the oppositely, the conjugate angular momenta. Remember, because of this issue of time reversal, if you are emitting into a left-handed medium, you need to check the absorption into the right-handed medium, and as you see, these two are very different for the same pattern of modulation. Of course, there is still a conservation law here. In fact, the two actually flip if you flip the modulation. This is similar to a magnetic bias. You see the same when you flip the magnetic bias.
Not really. Real-time reversal symmetry should have done that.
That's right, yeah. So this, essentially, we are synthesizing a magnetic bias. These effects are much stronger than what anyone has observed using magnetic bias, because we have a much stronger control over the tuning. So these are very large violations of Kirchhoff's law, but of course they still obey this issue that you are essentially, absorption and emission are equal at different ports, right? So you, for the same modulation pattern, you are emitting and absorbing in opposite-handed modes, and if you reverse the modulation, of course, you then absorb and emit with the same, through the same port. This is again a conservation law, but interestingly, from the formula that we derived to study these time modulated systems, we found that there are actually better ways of breaking Kirchhoff's law. In fact, in this scenario, it's a coupled resonator system in which now looks similar to what we built, but actually there are three independent resonators in which we modulate with different frequencies the coupling between them. You can actually fully violate Kirchhoff's law at a single port. So here there is only one port through which you can absorb and emit. There are not the two angular momenta that allow you to get that splitting, and still you can get drastically different absorption and emission patterns at different frequencies. So here you have a frequency in which the system cannot emit despite being almost a perfect absorber, and this is a system that fully emits despite not absorbing. There is still a conservation law apparently, but in frequency, right? Over frequencies, there is still this splitting. You cannot completely suppress this, and this is something still to be observed. But actually, Sander and Dimitrios came up with this also nice example of an actual optical system that the single port has emissivity and absorptivity completely detuned. And this is the full violation. This you cannot do with a magnetic bias. You need time modulation to achieve this type of response because you have a single port. The last comment I want to add here that actually connects nicely with these nice results that Vlad and Marcello were showing in the first day. Yes.
Can you do this with non-linear elements?
For the modulation. Absolutely, to drive it, yes. So this, yeah, all of these are based on nonlinearities, right? We use varactors to drive it. So the last question is, can we push this from tabletop radio frequency to optical systems? We have seen already results, very interesting results from Marcello and Vlad on using a single pump with a spin to bias an ENZ material, actually. To get Faraday rotation. Our proposal, was from a few years ago, was a little bit more complicated, but gives you a little bit more knobs of control over the response. So the proposal was to use the two pumps detuned with opposite handedness, and if you do some math, you can see that the pattern of nonlinearity in your material that is projected by the two pumps is a linearly polarized field that rotates at the speed determined by the difference frequency of these two pumps. So this, through a Chi3 simple nonlinearity, of course enhanced by ENZ or by resonances, gives you an anisotropy that rotates in time. And this basically makes the entire medium spin, exactly what we need to see some of these effects. With this trick, we have complete control over the speed. And again, there is no superluminal violation or anything. This is stuff that can work over very large areas. It's a uniform illumination. So you can actually control the speed, similar to what we've been doing with the phase patterns in our circuit. But you do get this effective bias of the system that can create Faraday rotation, as we speculated in this paper. And we are working on these experiments in which we used cavities in distributed Bragg reflectors to synthesize the right resonances, to pump them with different tenderness, and to realize in the resonant cavity this type of rotating medium that can enable some of these effects that I was describing, as well as others, for instance, Mario's ideas on chiral gain.
So, Andrea, is it Faraday or optical activity?
It's Faraday. So this is non-reciprocal, yeah. And in fact, you can also revert the pumps, and then you would revert the rotation, yeah. But this is what we expect from calculations. You actually can, basically you have again this opposite Doppler shift for opposite tenderness of the probe for given pump setting, and you can deplete completely the copolarized transmission. You can transform up to 20% of that into the orthogonal polarization, so create through just a single resonance a complete 90-degree rotation of the input pump. That is not reciprocal, it's Faraday. So this concludes what I wanted to show you. We have been making progress on these ideas of using this tabletop platform for space-time metamaterials. We are also exploring moving it towards the optical regime and use sophisticated forms of dispersion and coupling conservation laws to break some of the fundamental limits of these processes. And then this idea of using space and time for synthetic rotations and the associated phenomena. I want to thank several people, in particular the group members that have been working on this in bold. Adise, Luca, and Romain are all here that have been doing most of what I showed, and also Michele, Saitia, Enrico, Sedighe, and Nikita and Akshaj also been involved. Also former group members that have contributed a lot to these results, and collaborators from this collaboration and beyond. Many of them are here that have been working with us on these problems. And most importantly, all of you that came here and the people of the collaboration. Thank you.